Okay, so I'm going to attempt to provide a high-level overview of the database system architecture project. Really looking to get into how the different components are connected and which components we're actually looking at. As a disclaimer, I don't have a data science background, so this is my understanding. It's very possible that I'll say some things that are incorrect, and I do speak with confidence, which means that it might not be obvious when I say something that's wrong. If there is something in here that you pick up that's incorrect, send me a message, and I will make sure that gets out, or I'll just edit this so that we don't have incorrect information. But the intent by the end of this video is that you should feel comfortable or at least have a good idea of where the different components are that you're looking within the source code of Postgres, and some idea on how to find more information yourself, as well as what the process is to better understand this yourself. I think, yeah, that's the intention. So if you have that by the end of this, we're great. The actual project itself. So looking at kind of the evaluation or the different components of it, we're obviously going to be working on some sort of a range type analyze thing. There's going to be some selectivity estimation functions, some join cardinality estimation functions, and some benchmarking. The goal of the project being to improve the overall scheme of stats collection and cardinality estimation for range types. So specifically proposing and implementing this range type analyze, selectivity estimation for things that are overlapping or strictly left of, as well as a join cardinality for things that overlap. So the big picture here, maybe let's just start with like how does Postgres look at these things? Okay. So here's how I understand this. When we have some really big piece of data and we run a bunch of SQL codes on it, scripts, before we actually hit run, the SQL analyzer will go through and it'll take all of our descriptive SQL, which basically just says, hey, I'd like to select these things and join them with these things. And it creates a query plan. So that's where we had a relational algebra, and it'll say, okay, based on what Adam just wrote, these are the 50 different ways that we can actually make that happen prescriptively. So very specifically, step by step, how is the machine going to do the things that I asked it to do? And so the way that the process works is it'll develop a query plan, and it looks at all the different options and it estimates how much time will it take for option 1, option 2, option 3. Whichever estimate is the smallest, it actually goes and does that. So as a very simple example, you can imagine that I have two different tables, and let's say that I'm looking to do a join on the tables and then a select. So I'm going to take two tables, join them together based on some sort of a common ID, and then just select a small portion of them. Two ways that it can happen is either it can take these two tables, let's say they both have 4 pieces of data. First it joins them and then it filters out, filters things out and leaves you with one row. That's one way to do it. Or it can say, first let's do a filter and then let's do a join. And so the big concept is, the reason all this matters is because for every operation that you're actually pulling data, that costs resources and time. And what we're looking to do is limit the amount of time that it takes. The pieces that actually end up coming in to do all this estimation are statistics. So the statistics are coming in to actually do all of this work. If you kind of think about, some of what we were talking in class, the highest possible accuracy of estimation is to basically do the work, like to fully do and execute whatever the plan was. So let's say that one of your plans was to join first, then filter. If you want 100% accuracy on how long that's going to take, you would do the join, then do the filter, time it, and say that's how long it's going to take. But you can imagine that for a lot of these different functions, to do that for every single function defies the whole point. You're not saving any time. You're now just doing multiple queries you didn't need to do. So we need to find some way to actually estimate how long is it going to take to do the join and then do the filtration. So there's different ways that that's done. You might sample some of the information that you're doing. You might kind of extrapolate things. We talked a lot about histograms and how those are used, but essentially you're saying, I don't want to look at the whole piece of data. I just want to guess, if these are my 4 pieces of data and they've got salary, and you want to return everything that has less than $30,000 in salary, you want an estimate that's be able to return what percentage of your data does the computer think it's going to return for that select. And that's where the estimate piece comes in. So statistics are really the thing that are providing us the insight that are going to make our query fastest. They're estimating the time that it actually takes to complete. Let's get into try to understand this. So thankfully, there's a lot of hyperlinks, but I basically started with Postgres. So firstly, I needed to understand what is this range type. Thankfully, the Postgres documentation, I know it's been said before, but I'll say it again, it is really, really good. It reads well. It reads like a nice novel. It's not written in jargon. It's really well hyperlinked between different topics. So I would 100% say if there's anything that you're not sure about, start with the Postgres documentation. And then when they get into the specifics, go to the source code and just be using these two interchangeably. One kind of thing to note is up here when you're looking at the versions, make sure that you're looking at version 13. That's the one that we're currently working with. Version 14, if I just kind of do side by side, you can see it has some multi-ranges that aren't included in version 13. That's the difference. But I started by just reading through what is a range type. I can give you the Cole's notes is basically a range type. Rather than being an integer, it is a range from one bound to another. So I think there's a nice little piece that defines it pretty well here. All of your range types are going to have some lower bound and some upper bound. And then the other thing you'll see here, depending on what type of parentheses you use, it's either going to be inclusive or non-inclusive. And these are details, but that's basically your range type. So it can be a range of dates from date 1 to date 3. It can be from 9 a.m. to 10 a.m. It can just be a range of integers from 1 to 7. So there's all these different types of range types. One thing I think that was important or could be important in here was continuous versus step change. So you can imagine that if you're looking at a range of integers that go from 1 to 7, and you're looking to see, how many of those, or you're looking to see an overlap from 1 to 3, you know that there's a very concrete step from the number 3 to 4 when you're looking at an integer. If you're looking at time, there's kind of this idea of there's an infinite split of moments between each point in time. And so I think that's just something to be aware of, that with these ranges, there's continuous variables and non-continuous. Is this going to come up in how you do things? I'm not sure, but just so that you know that exists. So for me, I just read through this one kind of chunk at a time. As I came to something that I didn't quite understand, I would take it and kind of Google it or look it up. But for the most part, I would say that this made sense. Towards the end here, they got into the gist and the SP gist. So these are the indexes that are used for range types. However, within the context of our project, indexes are out of scope. So you don't have to worry about how is the indexing done. Indexing is looking at the side of the performance of the machine. So once you select the best query that you're going to use, how quickly is it able to execute that query. And we are not looking to touch the indexes, change the indexes, or use a different index. That's performance. We're looking at accuracy of estimation. So is our query plan doing an accurate estimation of how long it's going to take to do some different functions and actually do them in the quickest way possible from all of the options that we have? Yes. So I think after looking at everything on what is a range type, the next place that I went was actually looking to understand, how these different types are created or what these different types are. So every create type will have some different input and outputs. Specifically, input and output will always be included. They're a default, they must. Everything in the square brackets here in these definitions is optional. But then as you read through this, it actually defines every single, here at base types, it starts to actually define what is input function, what is output function, what's receive function, what is send function, and it goes through and defines. So again, I would suggest read through this and just understand how are these different functions made. This piece, I think for my initial, not as important, but again, it's just good to kind of understand when it comes to the building extensions. I think this is your building block for extensions. So all of this is very, very well documented here. And I think the next place that I went is actually looking at the analyze. Yes. So this analyze is where we're actually collecting statistics about our database. So the way that this works in Postgres is that when you load a table that has a column of, let's say, integers, Postgres is going to look at that column. It's going to say these are integer types, and it's going to generate statistics on that column. Statistics can include things like what's the maximum number, what is the count of different numbers, are there duplicates, how many duplicates are there, what's the average. So this is when we talk about these histograms, this is kind of where, in my mind, in my understanding, the histograms start to be created, or at least, sorry, the tools that are needed to create the histograms exist. So this is where you are building the math to say, okay, if I've got 1,000 values, I'm going to look at the mean, the mode. I don't know exactly how this piece works, but it's gathering these different stats of like, there's the number 20 is repeated 50 times, and it can start to provide you with the math and the tools that when it's time to estimate, and if you want to say, return me every value that's less than 21, and it already knows that there's 50 20s in your list, it's going to estimate how many rows are actually going to get returned. So this is kind of the meat of what we're doing is this analyze side of things. So again, I'd say read through the analyze section. Again, very well written. One of the pieces that he kind of touched on today is how the kind of vacuum and the vacuum daemon works. But essentially, I think what this is saying is that when you first load your data, it's going to do the calculations of statistics on every column. And then I believe there's some auto kind of vacuum daemon that exists that somehow knows when it should get triggered again. But if we are creating our own database, we are able to kind of determine when do you do one of these vacuums. So when you kind of clean up your database for rows that were inserted, deleted, and when do you do the analyze function again to recalculate things. The cost benefit is that it always takes time and it costs resources to do a analysis and calculate all these things. But if there's lots of changes in your database and you don't calculate it, then your estimations are going to be very incorrect. So thinking to our ETL project, for example, if you've loaded all your data and then there's all kinds of changes that are happening, but you don't reanalyze your database, the estimation is going to change. And so what might have been very efficient yesterday as a way to actually pull your data might not be very efficient today. So I think in a nutshell, that's kind of a lot of the Postgres content that made sense for me to kind of get into and understand. You can get into the descriptions of what are all the different comparison functions and operators, but I think this is more on the C code side of things, that it's more well defined and kind of explained. But coming back to the project now, so we kind of have a kind of an understanding of how SQL or how Postgres is going to take our script. It's going to look at different query plans. It's then going to use statistics to estimate how long each one of those query plans is going to take to execute. It's going to then choose the one that takes the least amount of time and execute it. One piece we talked about in class today was the accuracy. So the estimated time might be very low, but the actual might be very high. So how accurate is it in actually estimating the execution time? This is certainly something that we saw in TPCDS, that it estimated low number that ended up crashing our system. So accuracy is another important metric in all of this. So what does this mean? Overlaps, strictly left of, and overlaps. Overlaps is basically, is there some overlap between two ranges? So if I have a range of numbers from 1 to 10, integers, let's say 1 to 10, and then I have some other range that's 5 to 20, you can say, are those two ranges overlapping? That might be basically the ask. And in your SQL script, you might be saying, find me all of the rows where there's an overlap between column A and column B. And so it's going to say, all right, how many rows exist where there is an overlap? So that is the overlaps comparison that you're looking at. Strictly left of would mean how many ranges are there that are completely to the left of some other range. So if I have a range that is from 5 to 10 and another one that's from 2 to 3, 2 to 3 would be strictly left of or strictly smaller than 5 to 10. If there's some overlap, that it's 2 to 6, it would be left of, but not strictly left of. So that's the difference on that one. And then it's going to be the same thing that he's asking us to do for the join cardinality with overlaps. So selectivity and cardinality, what is this? In data mining, it seems like we're using the word cardinality a lot. Cardinality is the number of elements in a set. So if you have a range from 1 to 10, the cardinality of that set would be 10. There are 10 individual elements within the set of integers 1 to 10. That's all that cardinality means. Selectivity, the way that I've been thinking of it, is any place that we're going to do some sort of a filter. So for example, anytime that you say, select all of my rows from some table where salary is greater than some number, that's a selectivity function in the terms that we are selecting some subset of an existing table. So selectivity selects a subset, and then the join cardinality, usually cardinality seems to be used with join, but they're looking at how many rows are you going to return if you do some sort of a join. So if we do a join where there's a table that has 100 columns and there's another table that has 100 columns and we do a join, what are we going to estimate as the number of rows that we're going to return out of that? So that's the difference between selectivity and cardinality. We're basically going to be looking at building statistics and methodology to have better estimates for these two functions, to better estimate with greater accuracy how many rows will be returned when I have a select function, how many rows will be returned when there is a join function. So an example like this, for example, it's going to estimate, once it creates a relational algebra, it's going to estimate for every single one of these functions, what's it going to take. So this projection, this is a selection, how many rows would just that projection take? Once it's calculated all these things, how many rows is this join going to, I'm assuming that this is a cross product, how many rows is that going to give me? This query plan in particular is saying that it's going to do this selection on stars before it does the join. And so that's going to impact the query, but it's doing it for every single one of these moments. And so depending on which query plan I'm looking at, it's going to give me a different number, but we're essentially building the tool set that's going to be used to estimate the data pool for each one of these things. Coming back to the evaluation, range type analyze, we'll have to take a look at what is that. Then we have a selectivity estimation function. So these are going to be some sort of functions that are going to estimate selectivity when I'm doing an overlaps or a less than comparison. And then I'm going to be looking at building a function that's going to estimate the join cardinality, so the number of rows that are going to be returned for an overlaps. So the request is there's a join where there's an overlap of things. And then we have to benchmark. So now we can dive into some of the source code. So let's look at range types analyze first. I found that the comments in the code are actually really helpful too. So this really lays out that these are functions for gathering statistics from range columns. So again, this is a column by column statistics. So these are the way that I've been thinking about these is that type analyze is giving me the different tools that I'm going to use. How they're used and applied is going to be happening in these files with the funcs. So these are my function files. But the type analyze is the hammer, the saw, the nails, but actually making use of them to build a table and actually put them together is going to be over here in these other functions. So you can go through and take a look at, these are basically all of the things that we're calculating. I have not looked at this yet to fully understand what are the different stats that we're calculating. Just for reference, I'm using Microsoft Visual Studio Code. It's got a pretty cool feature where for a lot of these, if I'm trying to figure something out, I can hover my mouse over and it actually is able to pull some information. This one might not be the best example, but it actually pulls some information above it. So once you're looking at the cell functions, this has helped me a lot to actually be able to see like what is this doing. For some of these functions that I'm not sure about, I copy paste them into Google and then some Stack Overflow kind of stuff comes out and I'm able to read through there for some more information. But this file is basically the one that we would need to modify in terms of which statistics are actually being calculated on every single column. So this is the range types typeanalyze.c file. And then when we're looking at the select functions, when we're looking at the select functions, again, these are the functions for selectivity estimation for range operators. So again, anytime that we have a range, we're going to estimate how many rows are being returned when we're saying select. I shouldn't have two ranges. Select all columns that fit some criteria. In this case, the only ones that we're looking at is if the criteria is an overlap or a strictly left of. So each one of these is the functions that are being defined. For Visual Studio, if I hover over like a route bound B search, it gives me some documentation of what is actually being returned. I haven't gone through this specifically, but this would be the place to look at what is their methodology for actually returning some estimate of rows. That's where it exists. So we'll probably be getting quite familiar with all of this code once we go through, but I would encourage you to just kind of read through and start to try to understand. Usually, like for example, let's say that I don't understand how this is being pulled, and it seems to be getting asked of a lot. I would copy it, do a search, see where else it comes up. I think for this one specifically, it comes up in this document a lot. What I found is it usually ends up getting defined at the end of the document. Contains, I searched calc history selectivity. Here we go. So I was able to find, here's where it's actually being defined. This particular function is calculating a range operator selectivity using histograms of range bounds. Estimate is for the portion values that are not empty, not null. So it's obviously just calling not empty, not nulls, empties and nulls, and then it's going to be throwing them into a histogram. I'm pretty deep in it now, so there's other functions that have come before this that are returning some values. So how all of it works together, I'm not quite sure yet, but I know that it exists. So that's how I've been kind of working my way through understanding this. A much easier one to understand is the geoselect functions. So this is actually the join. It says up here, selectivity routines registered in the operator catalog in the Okay, this is actually not the best description, but this is the C code that actually describes how we estimate how many rows will be returned if we have a join operation. They're pretty clear here that they can't make good predictions on it given the stats they have. If you read through the C code here, they're basically saying that they will return 0.005 of the rows. So that's 0.5%. So basically the way that this is working right now is anytime that you have a join function that happens, the estimator will say, oh, you're joining to range types, If you're joining two range types, then the estimate that it will return is that you will be joining 0.5% of the columns, of the rows. And that is the number that it'll use as the cost of the operation, and that's how it'll calculate the different query plans to figure out which ones it should do. So this one might be a little bit easier to improve on because there's no real, there's nothing smart happening here. You'll also see that there's nothing being called. So there's none of the statistics from range types type analyze are actually being called and used over here. Whereas in the cell functs, a lot of the stats are being called. So in summary, when you have a data set and you run a query on it, before the query is run, all of your descriptive SQL is going to be translated into a bunch of different relational algebra into prescriptive SQL that says exactly step by step what are the different ways that we can execute that. Each one of those prescriptive plans is going to be estimated using some statistics. It's going to estimate how long is it going to take me to do plan A or plan B or plan C. Once it calculates all those numbers, it's going to compare them and it's going to say this one's the fastest, let's do plan B. When it runs plan B, it pulls all the stuff. It's going to have an actual, how long did that actually take versus how long did I take to do it. And that's the whole idea of query planning. The different files that are being kind of called and pulled on are first the type analyze. Anytime you load data into your database, the statistics on every range type column will be calculated using this code, and they will then be attached to that column. So anytime you are running some sort of a function that involves that column, it has all those values pre-calculated that it can use in estimating. When it comes to a select function, in terms of creating some sort of a subset or doing some sort of a select on a table, it's going to go to this C code and it's going to look at all the different options, pull in those statistics that were calculated, and it's going to figure out what the actual ratio or number of rows is going to be returned. So the output of this is some ratio, some number that's like 5% or 10%. It'll say, based on what you're trying to do over there, we estimate you will return 10% of the rows. And then it can amalgamate that into the rest of the relational algebra that's happening. If you're doing a join or looking at the cardinality, then it's going to come into this and it's going to say, oh, you're doing a join on a range type. We estimate 0.5% of the rows will be returned. So once we change up these things or do something, we then benchmark it. So we'll have to find some way to take some data set, run some queries on it before and after, and see how long does it take with what exists today versus how long did it take with what we have developed. Part of the conversation today as well was looking at the accuracy. So how accurate was your estimate compared to what really happened. So like I said, we're not focusing on indexes at all. The accuracy of the estimator is how many tuples were returned versus the actual returned. We are looking to improve the optimizer estimation, not the performance. We might have a little bit more of a load up front on estimating things, but this is where we talked about changing the existing statistics so that they can be reused and used rather than just slapping on a different statistic. On the implementation for the grading is basically does it work, kind of a yes or no, or how well does it work and how efficient is it. This was not a binary mark, so it could kind of half work and it could be not really efficient, but that's how you'd be graded there. So really the focus should be 50-50 on the theory and the implementation. If you have great theory but you can't apply it, then it's useless. And if you have terrible theory but you apply it and it doesn't work, also useless. So somewhere in the middle is where to focus on. I think that kind of covers it. That's really the crux of what we're trying to accomplish here. I think as we go through, we'll probably start getting into more of the details and how these things work. But please let me know what I got wrong. If there's anything that was incorrect in what I said, please correct me on it. Hopefully this helped a little bit. But I'm sure as we all progress through this, it'll make more and more sense. One thing I'll point out, just timing wise, this project is 40% over course mark. Some of the other projects we're working on, like TPC-DS, is 15% of our course. So weigh your time effectively and make sure you're putting your time into the place that matters most. Cool. Thanks, guys.